Hello, everyone. Thank you so much for that kind introduction. It's really a pleasure to be here this morning. So this morning, I'm going to talk to you a little bit about how we can unlock more value through carbon mineralization. There's been more than 2 decades worth of work that has gone into advancing subsurface carbon mineralization to the point where it is right now, largely thanks to the Carbfix community. But the challenge that I'd like to pose to the audience here is really in terms of how do we innovate while managing the need to meet the rising demand for energy and resources while coupling to beneficial climate impacts. So what I mean here is that the beneficial climate impacts effectively come from subsurface carbon mineralization, but now can we actually start to couple that with the need to meet a rising need for critical metals, as well as geologic hydrogen, for example. So that really sets the stage for what I'm going to be talking about this morning. And before I do a deep dive into some of the science aspects, I kind of just wanted to zoom out and just remind ourselves why we're all here. We're all here because we've had the privilege of having access to clean air, clean water, healthy soil, and a stable climate. These are really the fundamental building blocks of life, but at the same time, abundant, low cost, and clean energy is crucial for realizing a high-quality human life. At this juncture in time, the question that we as a society are facing is how do we reconcile these needs in response to a rapidly changing climate? And luckily for us, the IEA has actually come up with this really nice roadmap in terms of achieving net zero emissions by 2050. And the community that we have here has largely worked towards advancing carbon removal solutions, as you can see here. Right, so there's been decades and decades worth of work. There's also been several publications on subsurface mineralization, including taking some of these solutions to scale and coupling with direct air capture. And so when we look at the current state of the art, we've largely uncovered the influence of mineralogy on carbon mineralization. We've unpacked the kind of mineralogies that are suitable for more engineered, short-term, accelerated carbon mineralization. These typically tend to be some of the ultramafic-rich rocks, as you can see from here. And then we also have the earth-abundant basalts, right, that have a lot of aluminosilicates in them. We've basically been able to convert the earth into a reactor system that we can tune to store our CO2 emissions. We've been quite successful in that. But what we've also noticed in the course of doing our science is that a lot of the energy-relevant metals, like nickel and iron, are actually co-precipitated with the carbonate phases. And so the challenge here is figuring out how can we actually prevent the co-precipitation of iron and nickel along with the carbonates, so we could have one stream that is actually concentrated in the energy critical metals, and we have another solidified co-product, which is effectively our carbonates. So then the overarching science question that we'd like to address is how can we tune the fluid interactions with mafic and ultramafic rocks to enhance the recovery of energy critical metals and produce geologic hydrogen. So we'll tackle this one piece at a time. So first I'll talk about the critical metals piece, and then we'll move on to the geologic hydrogen piece. And so what I'd like to do this morning is to really acknowledge the fact that carbon mineralization, we as a society or we as a community have brought it to a point where we can safely claim victory in the area of the carbon removal space, but there are some unanswered or unexplored aspects of coupling carbon mineralization with our ability to decarbonize the supply chain of energy critical metals, as well as decarbonizing hard-to-abate industries, right? And if we were to decarbonize critical metals and materials, then effectively that aids in tripling the renewables capacity. And by being able to produce geologic hydrogen at scale, we can also help decarbonize heavy industry like iron and steel and cement, right? So harnessing the subsurface to our advantage is really important and crucial, and a community like ours, with the collective intelligence that we have, I think can certainly make a dent in this problem. So what is the base case, right? So we're all engineers, and we all ask ourselves, okay, where are we starting from? And the point where I started from was actually as a PhD student at Columbia University, where I worked with Jörg, Peter Kalaman, as well as Alyssa Park. And we did some of the earliest studies comparing and contrasting the influence of temperature, CO2 partial pressure on the reactivities of mafic and ultramafic rocks. And what we found was that in a finite time scale of just about 3 hours, we are able to unlock a lot more reactivity out of olivines, as you can see here, compared to the basalt, as you can see here, right? And what we found was that a lot of the magnesium and the calcium actually gets locked up in some of the clay phases. We are able to get mineralization, except with, in the case of olivine, we get a lot more of the magnesium carbonate formation up front. So then these questions, and so I did my PhD, I showed this data as part of a PhD thesis defense, and I was left with this lingering question of how do we actually try and partition the iron and nickel that is co-precipitating with the carbonates, right? And so that really motivated a big portion of the work that I have been doing over the course of the past couple of years. And so this motivated me to start tackling the challenge of coupling carbon removal with our ability to decarbonize the critical material supply chain. So here's the vision for how we'd like to approach this. So I first started looking into this. I had a visiting student, Shreya Kathre, from India, and she came to me in 2021. And so we worked out a project where we started to explore how we could use chelating agents like EDTA, so that way we could chelate the nickel, pull that into the solution phase, and just mineralize only the calcium and magnesium components. And then a year later, Todd Sheff called me up and he said, well, Greeshma, there's this ARPA-E-FOA. Can we put together a really cool concept? And so we worked out this concept together, and this is actually the picture that I took from the ARPA-E minor project that Todd and I are part of. So long story short, the idea here is that we would inject a solution that has some of these chelating agents of interest, so we can preferentially pull some of the energy-relevant metals of interest into the solution phase, and then we can mineralize the calcium and magnesium into a solid carbonate form. And so this is the work, some of the earliest work that Shreya had done. So she brought with her some serpentinized peridotite rocks. And what we did then was to actually introduce EDTA into the solution, along with sodium bicarbonate solution, so that way we could balance the pH. And what we found here was that interestingly, this serpentinized peridotite has, of course, a lot of serpentine, has a fair amount of olivine, but a hypothesis here was that we would be able to solubilize the metals, and we would be able to mineralize the magnesium and form magnesium carbonate. And turns out we are able to do that. So if you look at this rock here, this is the unreacted rock, and then after mineralization, we actually see these really nice magnesite crystals, and we also see these silica-rich amorphous phases, right? And what we also see is that the surface area of these particles effectively decreases because we grow a lot of carbonates, but also the particle size increases. It increases by almost 3 times its original size. So these findings were really interesting. And now when we actually look at the results, what we see here is that when we run these experiments, if we focus just on the purple bars, these are reactions at 10 hours, 50 bars of CO2, and 185 degrees centigrade for 10 hours. We get extensive mineralization that are to the order of about 70 to 80%. And we're able to recover about 80% of the nickel into the solution phase. And the iron, we have only about 40% of that, and we effectively don't have very much of manganese and chromium in the solution. So these results were very promising, right? And then we asked ourselves, okay, so what are the actual associated mechanisms? And what we find here is that we have both serpentine and we have olivine. And when we actually put this through a dissolution, our coupled dissolution and mineralization process, the layered serpentine structures are the first to actually disrupt, if I may. And they're the ones to actually release the magnesium and all of these other energy-relevant metals into the solution phase. And then we have the olivine that then starts to get altered. And effectively, we end up with this product system here that is rich in magnesium carbonates, but also has the amorphous silica in it. And then recently, I had 2 other students join my group, and this is for the ARPA-E project that I'm on with Todd Schaaf. And now we started to explore a whole bunch of other ligand systems. So we started to look at EDTA. There's another one called EDDS. And so the hypothesis here was that, is it possible for us to only extract the nickel and leave everything else in the subsurface environment? Or in other words, more broadly, is it possible for us to extract only the manganese, only the nickel, or only the iron, and just leave everything else in the subsurface environment? If we could, that would be nice, right? And so we ran these experiments with twin sisters olivine at a wide range of experimental conditions. So if you look at 50 degrees centigrade with EDTA, you'll see that we produce a lot of manganese at low temperatures. We solubilize a lot of it, but then the extents are below about 40%, and we get about 30% nickel and iron. When we do this with EDDS, we effectively suppress manganese release. And that was quite interesting. But we still continue to get a fair amount of nickel yield, which is this green. And we also get about 40% mineralization. Interestingly, as we go to 90 degrees centigrade, we're able to get up to 80% mineralization. And we effectively also see a fair amount of nickel leaching here, as you can see. But then, with the use of EDDS, we suppress all of the manganese leaching. And we almost exclusively have nickel in the solution with a little bit of silica, and with a little bit of iron, if I may. So these results are very, very interesting. And then I thought I would just stop with this slide, but then I was speaking to Sandra, and Sandra had indicated that it's very easy for us to get to very, very high temperatures in the subsurface environments, right? So I thought, well, why don't I also show the results for 120 and 150 degrees centigrade? And so at 120, we get close to 100% mineralization, and more than, I want to say, 80 to 90% leaching of the nickel, and we suppress most of everything else, right? So these results, and we get very similar results also at 150 degrees centigrade with EDDS. EDTA is a little less selective. With EDTA, we get both the nickel as well as the iron. So these results are slowly starting to unpack for us how we can start to leach some of these metals into the solution phase while actually mineralizing the calcium and magnesium. And also, if we can leave more of the iron behind, might that actually help facilitate geologic hydrogen production, right? So these are some of the questions that started to come up. Now, I know that our community here works quite extensively in basalt, so I thought I'd show a few results with the basalt samples that we have. So we actually did work with picritic basalts, and so we contrasted the serpentinized peridotite, which is what I showed earlier, with olivine gabbro and picritic basalt. And with the picritic basalt, when it's altered at about 155 degrees centigrade, we produce a fair amount of disordered dolomite as well as magnesium calcite. And at slightly higher temperatures, we produce a fair amount of magnesite as well as dolomite. So these results are actually quite interesting for us. And it turns out that the extents of mineralization, they scale with the olivine content. So as you can see here, we have relatively low olivine content compared to serpentinized peridotite. So extents are on the lower side. But the results that I'll show you on the next slide actually indicate that even though extents may be lower with picritic basalt, the metal recoveries are actually really quite impressive. So if we just focus on this data here, which is experiment 385 and 50 bar, with iron, you'll see that we're able to get up to 40% iron leaching with the picritic basalt, about 60%, close to 60% leaching of manganese, 40% leaching of aluminum, and 60% leaching of chromium. The fact that picritic basalts have all of these different energy-relevant metals, and the fact that we're able to recover them in the solution phase is actually quite surprised us, really. So we are working on getting this. This paper is actually in review at this point in time. So then the engineer in me asked, okay, great, we are leaching a lot of these metals. Once the solution comes back up to the above ground, how do we actually separate out all these metals, right? So we started to develop a material separation platform. So effectively, what we started to do was to develop sorbent materials instead of using solvent extraction, because sorbents tend to degrade a little less. They're also a little bit more environmentally benign compared to solvents, right? Organic solvents. So what we did was we took a silica substrate, as you can see here. We tethered that with a linker, and then we tethered the linker to our active functional group. Now, we chose this functional group here because it can also work for electrochemical separation as it does for conventional pH swing type of absorption-desorption mechanisms. And from these data that you can see here that we're able to get nickel separation up to about 90%. And if we have cobalt and iron in the mix, it's actually much more selective for separating out nickel. So I just wanted to give you this one example, but we have a whole suite of materials that will selectively pull nickel, cobalt, iron, manganese, chromium, and zinc as well. So we are working on this material slate, which is effectively switching out this linker, switching out the linker and switching out this functional group so we can get very selective binding of the metals. So with this, I quickly wanted to summarize the findings from this part of my talk. So effectively, what we've gone on to show is that there is feasibility of solution mining coupled with in situ carbon mineralization. This we have established experimentally. If we succeed in taking this to scale, this effectively eliminates the generation of mine tailings, which is so important for the future of the world, right? There are so many disadvantaged communities that grapple with the challenges of mine tailings, so if we can eliminate that, that's a huge benefit. And this is just a quick summary of all the key experimental results that I showed earlier. And just to quickly summarize, even at 90 degrees centigrade in the presence of EDTA, we are able to get extents of about 80% and about 60% recovery of nickel. There are opportunities for preferential recovery of manganese as well as chromium, as I have shown here. And there are opportunities here for only extracting the nickel while leaving all the other metals behind in the solution phase. So now what I'd like to do is to talk to you a little bit about how we can decarbonize hard-to-abate sectors as well. So in addition, so hopefully I've convinced you now that we can couple carbon removal with the decarbonization of critical metals, and if we can try and decarbonize hard-to-abate sectors, that would be quite compelling as well. So just to give you an introduction to stimulated geologic hydrogen, a lot of us have seen the serpentinization reaction here. So we start with olivine in a hydrothermal environment, effectively converts to serpentine. We have some brucite. We produce iron oxide, and there's a lot of hydrogen that is co-produced. So this reaction typically takes place at elevated temperatures, right? 200 to 250 degrees centigrade, that's what's been reported in the literature. But there's been a lot, and we are seeing in our lab the potential to produce stimulate geologic hydrogen even at 90 degrees centigrade. There is a subset of conditions that we can tune to get there. It's in the early stage, so I won't delve into that, but I'm happy to talk about it later. But the key things to keep in mind about geologic hydrogen is really the content of fayalite we can actually have. So this figure here actually shows pure fayalite. So if you have pure fayalite, when we produce geologic hydrogen, most of that hydrogen is in the gas phase. But then as we start to increase the phosphorytic content, a lot of the hydrogen is actually dissolved in the water. So the question of water-hydrogen separations also becomes important, especially if you're dealing with phosphorytic-rich rocks versus phayalitic-rich rocks. And then another key consideration is the influence of nickel. So there have been some past studies that have shown that when we have nickel co-precipitated with iron hydroxide, we see a significant increase in the hydrogen yield relative to just pure iron hydroxide alone. And so I'll talk a little bit about geologic hydrogen potential and proposed goals. So again, the engineer and me wanted to do quick back-of-the-envelope calculations to get a sense of how feasible this would be. So we started to look at olivine bearing 50% phosphorite, 50% fayalite. And we took a field site estimated to be about 40 kilometers squared in depth and about 2 kilometers in 2 kilometers in width, if you would. And so the estimated volume is about 80 kilometers cubed. And from this region, if it has about 50% forced-derived 50% phayolite, we're able to get up to 223 million tons of hydrogen, just theoretical maximum, right, if we serpentinized all of it. And even if we only serpentinized 10% of it, we would still get 22 million tons of hydrogen. So that's really, really promising. So then we started to propose a few goals. So this is our baseline. Our baseline is to be able to produce hydrogen at the cost of $1 per kilogram and with CO2 emissions of 0.45 kilograms of CO2. And our proposed goal is to make enough technological advances so we could bring down the cost to less than 80 cents per kilogram and also reduce CO2 emissions to about 0.4 kilograms of CO2 per kilogram of hydrogen or less. And then we started to look at the different ways in which we could stimulate hydrogen production. And there's two ways to do it. We could either introduce water or we could introduce steam. And I say this because here in Iceland, I would say you're blessed with having geothermal gradients that can actually, so if you just put in water, you're able to actually have steam in the subsurface environments that is really favorable for serpentinization. But in other parts in the US, such as the mid-continent drift, that's not the case. In those scenarios, we actually just have to inject steam instead of injecting water. Injecting steam is not cheap, right? So where we really take a hit, so the drilling costs are very similar, hydraulic stimulation, pumping is all of this is very similar, but when it comes to chemical stimulation, steam injection tends to be more expensive compared to water injection. And then when we add up all the total costs, water injection tends to be cheaper compared to steam injection. And this is really a function of the geologic formation that we are working with. And what this tells us is that effectively with these costs, we're able to break even if we have steam injection, but if we have a water injection, we actually turn a small profit of about 28 cents per kilogram of hydrogen. So this got me a little excited and optimistic about being able to harness these reservoirs for geologic hydrogen. In terms of the carbon footprint, we started to basically lay out the different scenarios associated and all the different operations associated with greenhouse gas emissions. And so the greenhouse gas emissions for drilling, hydraulic stimulations, proppants are all very, very analogous to that of geothermal production. But then where the nuance comes in is with the stimulation, the production, the injection, right? So that's this bar here, right? So when we add up all of these contributions, then effectively we have about 0.45 kilograms of CO2 equivalent per kilogram of hydrogen. So these numbers, again, got us excited because if you look at the CO2 emissions associated with blue hydrogen, they're typically in the range of 3 to 4 kilograms of CO2. This is with 93% CO2 capture. With green hydrogen, it's in the neighborhood of 2 to 4.4. And with stimulated geologic hydrogen, it's about 0.45 kilograms of CO2 per kilogram of hydrogen, right? And so these numbers really compelled us to start new projects in the area of geologic hydrogen. So with that, we are here as a very vibrant community that has really made significant strides in being able to harness the Earth as a reactor system for climate solutions. But now can we start to harness the Earth as a reservoir, not only for climate, but also for energy solutions? When I say energy, I'm talking about geologic hydrogen, as well as for critical metals and materials. But in order to get there, there's still some open questions that I'd like to pose to this community. And the first question is, how do we actually stage a reservoir engineering operation to stimulate geologic hydrogen production, co-recover energy critical metals, and store and mineralize CO2? This is one way to help maximize the value of the reservoir. The second question is, how can we tune these co-recovery pathways for high-pressure CO2 injection versus injecting water with dissolved CO2? The third question is, what is the influence of mineralogy, fluid composition, and temperature on geologic hydrogen stimulation? And the fourth question is the fact that geologic hydrogen is stimulated in the presence of energy-relevant metals like nickel and iron. But critical metal recovery will actually deplete these metals that we need for geologic hydrogen production. So these are contradictory conditions, right? So how can we actually tune the subsurface environments or perhaps stage a reservoir engineering operation in such a way as to co-produce both the energy relevant metals and perhaps leave a fraction of those metals behind so we can also stimulate geohydrogen production. And the end of life, perhaps, convert that reservoir into something that can store CO2. So with that, I'd like to acknowledge my group members. Here are some of the group members who are actively contributing to these technology development efforts in my group, as well as their funding agencies. I know that we have 10 seconds, so if time permits, and if the moderators permit, I'd be happy to take any questions. Thank you for your time. Yes, Carrie?
Thank you, Greeshma. I was wondering, since the capture plant I showed yesterday, where we're actually producing over 95% geological hydrogen after scrubbing out the CO2 and the H2S, a considerable effort and probably cost is related to actually purifying it to a form where you actually can store it in a meaningful way. So did you look at these costs when you were looking at the costs of actually producing a geological hydrogen in your plot?
That's a great question. So we only looked at the cost of stimulation. We did not look at the cost of separation, right? And there are many ways to separate and store hydrogen. I'm happy to talk to you about that. Perhaps the most durable way and the easy way is to actually store the hydrogen in the form of a solid and then transport it to whoever needs it and wherever it's needed. That's one strategy. Another strategy is, maybe convert it to electricity, maybe put it into a fuel cell, but then again, you're really not maximizing the value of the hydrogen. So perhaps if you can supply it to an industrial facility, that might be the highest value. But there are several scrubbing technologies to actually do the separation. I'm happy to talk to you about that offline. Great. I think we're up on time. Okay, great. Thanks, everybody.